Say hi, Milo. Welcome back to the Andromedoom devlogs, episode number 10. If you've made it this far, congratulations. I've shown you how to build the prototype I showed you back in episode 0 from scratch. Not every tedious detail, but you have all the tools to replicate what I did. In this episode, I'll be showing you how to build Leviathan, which is the boss inspired by Terraria's Eater of Worlds. I'll show you a quick demonstration of that. I'll show you the implementation I used in the prototype, which is just procedural. It's quite messy. And the proper implementation using the finite state machine that I showed you how to build in episode 6, which is the way that I'm building it in the main game. It's coming up. Let's switch over to the screen. So let me show you what it looks like in the prototype first. Start spawning from the top. Now the head aims for the player, right? If you split the worm, you get a new head. If you shoot at the body segments, they shoot straight down, and the worms eventually stop at a certain height. They won't go further, so their boss doesn't land. The aim is just to hit the player. I'm going to show you how this is implemented in the script for the prototype, which is procedural in nature. So the boss scene itself is just a kinematic body with the boss script attached. It's got a collision shape and a mesh. On the boss script, there's a mesh array, a Godot array, which keeps track of the 3 different meshes: the head, the body, and the tail segments. Let's look at the script. And as you can see, it's a mess. Lots of fields. The ready function isn't too bad, it just initializes everything. Process function is just one giant block. And basically it checks if the current segment's ahead. If it's not, it moves a certain way, and it checks collisions. And then we've got a bunch of functions here. One to change direction, one that takes damage, one that destroys the head, and so on. And basically the code that I'm going to take you through step by step is almost identical to this, except instead of using a bunch of if statements, it'll be using the finite state machine. So I'll show you the finite state machine. In case you haven't seen that episode, I'll give you a rundown. I've got a patterns num sub namespace. So we've got a class, a state class, which takes a generic parameter, which is the type of object that utilizes a state machine. Each state has a reference to the state machine that contains them, the node that uses them, and it has an enter and exit function when the state machine changes states. And of course it has its process and its physics process relevant to that state. So when a node, kinematic body, whatever it is, implements a state machine and it calls its own process, what it does is it delegates that to the current state. It's just one line that says execute the state process function. Now the finite state machine class is basically a dictionary of states, where you access a state by passing a string. That's the key. It keeps track of its current state, has a reference to its node, and has a method to add new states, set the current state. Okay, let's begin by setting the scene. So on the UI and level selection episode, we set up the Tokyo level, which is just a carbon copy of the Sydney level, but it doesn't have the shields. Okay, this is where we'll start on this Tokyo level. Now what we want first is a spawner for the boss. We don't want him to be created instantly. Let's do that first. Let's add a child node call this Leviathan spawner. And we'll move this around here. What we'll also do is aim it a certain way. So the camera's facing this way, the boss will come at an angle. I'll explain why this happens later. Next, let's set up the boss scene. Add a new 3D scene. Change the type to kinematic body. It needs a collision shape. It needs a mesh. There's 2 ways you could do this. The first is you can add all meshes directly underneath this node and hide the ones that are irrelevant. Or, as I showed you earlier, you can keep the meshes in an array attached to the main script and then swap out the mesh property on the mesh instance node. at runtime. I'm going to do it the other way, and the reason is if you've got animated meshes, this way works a little bit better because you don't have to worry about swapping out the skeleton and the animation player and things like that. Okay, then we'll load the meshes. Now remember, the Godot convention is -Z is forward. So it's best to rotate these such that this arrow points towards the back. Cool, let's save this. Okay, now we'll add a collision shape to our alien. Okay, now we'll attach a script. A new C# script, kinematic bodies. Now recall in an earlier episode I created a destructible inheritance hierarchy. So for example, our little alien invader also inherits from destructible. So it has the functions take damage and destroy. I'll show you that quickly. This is the destructible class, and it has functions for, taking damage, destroying, and shaking the camera. That's from an earlier episode. I can link that in the description below. So we're going to inherit from destructible, and we're also going to implement the iDestructible interface. So first thing we want is a finite state machine. So here we can say using Andromedoom tutorials.patterns state machine boss finite state machine. So let's begin with initializing it. We can say finite state machine is a new finite state machine of the type boss, and the state machine needs a reference to the class that's implementing it, so we're passing this into the constructor. Now what we want to do is create a bunch of states that the state machine implements. So what I'm actually going to do here is create a new folder called boss, and the Godot editor, let's save this just to be safe. We'll move the boss into here, and in this folder I'm going to implement each state as a separate script. Okay, so as you can see, I added a bunch of keys here. It describes the different behaviors of the boss at any given time. Now if it's the head, it's moving independently. If it's the body or the tail, it's following ahead. Boss turns, the head also turns, it drops level, so it flies lower, it fires, and it destructs. And each of these classes are in their own script. For example, boss moving, and it inherits from the state generic class with a boss generic parameter, and so on. Now every physics process for this boss, okay, physics process, we don't explicitly specify what it does on each physics process. What we do is we ask the finite state machine to execute the physics of the current state, and you need to pass in the delta parameter here. Ditto for the regular process. Okay, also in the ready function, let's get a reference to the mesh nodes, but we'll store them in a dictionary. So let's say using system.collections.generic private dictionary. We'll pass a string, and here we'll pass a mesh instance, and we'll say meshes constructed here. Say meshes.add, this is just the standard dictionary. We can say head, and here we can say get node type mesh head, mesh body, and mesh tail. And we need to cast it to this mesh instance type. Now, how does a segment know if it's a head, a body, or a tail? The way it works is it's like a double-sided linked list. Every segment has a reference to the segment in front of it and the segment behind it. So we'll create those now, references. So private boss, oops. This one we'll call segment in front, segment in back. Now we'll actually set this to public, so the spawner can set these references. So what we want here is a function, or is a method that checks to see if there is a segment in front or in the back. And in doing so, first set the visuals, in other words, which meshes to hide, and what the current state in the state machine should be. So we'll say public void update update segment. What we can do is make everything hidden by default. So for each, we can say mesh and meshes dot values. We can say mesh dot visible equals false. This just toggles this, sets it to false. And here we can say if segment in front is equal to null. In other words, if this is a leading segment, so it's a head, we can say meshes head dot visible equals true, and we set the current state to moving, else. Now if there is a segment in front, this won't execute, so it's not a head. But what we want to check next is if it's a tail. So if segment in back, or segment behind is no. So if neither of these references are null, it's clearly a body segment. So on the ready function, we're going to say update segment. What this does is it sets the visibility of the appropriate mesh, and it makes sure that there is an initial state. So keep in mind that if you don't set an initial state in your state machine, you might actually crash your program. But this is taken care of in this update segment method. Okay, first thing we're going to do is move the head forward. So in the boss moving state, let's go into physics process. Now the reference to the actual boss segment is in a field called node, as defined here, public T node. When this state is created, the node is assigned to whatever the state machine is referencing. So here we know the node is of the type boss, which eventually inherits from kinematic body. So we know it has the move and collide method. And we're moving forward, so negative Z. So minus dot node, transform dot basis dot Z. Remember, this moves along the local forward axis. And here we multiply by delta. And here, well, we need a movement speed. So let's go back to the boss. And typically you'll want to export these fields so you don't have to come back to the script and change them. So use the export attribute so it appears in the Godot editor. And we can say private float movement speed, and we'll say 1.5 units per second. So, movement. Well, this has to be public. A lot of these may better be implemented as properties with public gets and private sets, but we'll leave it as it is for now. Okay, it moves forward. Let's test this and see how it looks. And as you can see, he moved forward and collided with the wall. The segments are very big, so I'm just going to shrink it. Yeah, that's more like it. Okay. Now let's take a break from programming the boss and we'll program the spawner instead. So here, let's attach a script. Let's export a private integer. Call this boss length. And let's default it to 8 segments. Here we'll say private float, spawn interval. And we'll say we'll spawn a segment every 1 second. There's 2 ways you can do this. One is just keeping track of time in a field and then incrementing that field with delta. And if the time difference exceeds the spawn interval, then spawn again. Alternatively, you can use an asynchronous method. I'll show you how to do that. So void spawn, and here we'll say await. We can say await to signal. Okay. Say get tree, create timer. It takes the interval. And basically we're awaiting the timeout signal. So initially we're waiting for the timeout signal. Creating a timer, once it times out, it sends the signal and it frees itself from the tree. And we basically want to do this for the boss length. Integer I equals 0, I is less than boss length, I plus, then what we do? Export a packed scene. That's the boss scene. You can say boss scene. And here we'll get parent. We won't attach it directly to the spawner. The reason for this is, although we want the boss to initially take the direction of the spawner, we don't want it to be parented to the spawner because all of its local transforms will be transformed by the spawner's position. But when we go to the parent, which is this aliens node here, it doesn't have any spatial nodes. So its local space transform and its global space transform will be the same. In other words, everything is centered around 0, 0, 0 with no rotations. It's not strictly necessary to do this if you're very fastidious about using global versus local coordinates, but it's a bit defensive to do it this way. Get parent, add child, and we'll say the boss scene. Well, actually, we want a reference to it first, so we'll say variable boss instance is equal to the boss scene dot instance. So we've created the instance of that scene. We're adding it into the scene tree as a child of that alien node, that parent. You can say this as a spatial. Once we've added it to the tree, what we can do is set the instance dot global transform equal to this global transform. Now once this is looped 8 times, we can free the spawner. So let's come back here, hit build. We've got the length, the interval, and the scene, which we need to port over here. It's the boss scene. Let's test this. Ah yes, we didn't call the method yet. So let's go back here. You can say public override void ready and call spawn boss. Probably a better way of doing it like this. Okay, let's try again. As you can see, there's the 8 segments incoming. Of course, they're colliding with each other at this point. Very good. Now instead of instantiating them as spatials, let's instantiate them as bosses. What this gives us is access to the fields regarding the leading and the trailing node, and the update segment function, which I don't think we'll need it in this instance. So here we'll create a local variable. We'll say boss previously spawned segment. This will be null. And here we'll say if previously spawned segment is not equal to null, you can say the previously spawned segment segment in behind is equal to this new boss instance. And we might have to initialize this to null explicitly. Yes. And then we say boss instance dot segment in front is the previously spawned segment. Then we say previously spawned segment is this one. When we add this as a child, it will call the update segment method. So it will update its visuals. Also, one more thing you want to do here, update segment on the previously spawned segment, because that previously spawned segment has already had its ready function called when it was added to the scene tree, and it's already updated that segment, so you need to call it again. So the first one's a head. Now you can see the segments spawning on top of each other, but we know it's working because the tail is spawning and the bodies are spawning. The reason they're not moving is because we haven't written the following function. It's because we haven't fleshed out the following state. So let's go to the boss following state. You can say public override physics process. So we want to point to the segment in front of us. And the way to do that is you take the origin of that node, take your origin and subtract the two. That gives you a vector that points towards that point. So here we'll say move target. This is equal to, so the node, which is our current segment, and we'll say segment in front dot global transform dot origin. It's a bit verbose, but we'll say node, so our node, global transform dot origin. So that gives us a direction to the leading node. And we'll say node dot move and collide to the move target, multiplied by delta, multiplied by the movement speed. And then the other thing we want to do is make sure that we're pointing towards it. This will become apparent when it starts turning. At the moment they're all pointing in the same direction anyway. So we'll say node dot look at move target, which is global anyway. No, because that's a relative vector. What we actually want is just to look at the node in front. So we can say segment in front, like that. And that takes the other parameter, which is the vector3 dot up. We'll just pass the basis y, so the local up direction. Dot basis dot y. Okay, let's test this. There you go. And the good thing about this is the further away the segment, the faster it catches up to the segment in front. That's because the greater the distance between them, the longer that move vector. So you don't ever have to worry about your segments being too far apart, they'll catch up. If you adjust your box collision shape, you won't have those large gaps. So that's the segments of the boss spawning. Next we'll see how to turn the boss. At the moment he's slamming into the wall and technically still going forward, but he's jammed in the corner. What we want is a turn that bounces off the walls. Okay, before we write this class, let's add a tween directly underneath the boss. You can do this in script, and I showed you how to do this before in the finite state machine episode, but we'll do it this way instead. So let's go back to the boss and we'll say here, private tween, or it should be public. And in the beginning we'll say tween equals get node, call tween, and we'll get it of the type tween. Let's go back to our turning class. Okay, now when we first change state to the turning state, we want a new direction along the XZ plane. So we're turning in the XZ plane. So here we will create a vector 3, new direction. And within the enter function equals to new vector 3. Now the X, go GD dot random range from -1 to 1. But we need to cast this to a float. 0 in the Y. And similarly, we take this line of code, so random Z. So that's our new direction. And because we're turning multiple times, it's a good idea to reinitialize this back to 0 every time. And we also want to interpolate from the old direction. Now the old direction is just the origin minus the Z basis, the forward direction. Okay, now the tween, well, node.tween. There's two ways you can do this. You can do this through interpolate property, but that's very difficult because you have to update all the other vectors. The best way to do it is with interpolate method. Now, as mentioned in the other finite state machine tutorial, interpolate method can only take one argument, but the lookout function takes 2. So you'll have to create an auxiliary method with only one parameter that you can then pass into interpolate method. So let's go back to the boss script here. We can create this function, or this method, public void lookout, and we'll call it upwards. And it takes in a vector 3 called direction. What this actually does is it just calls the lookout function towards the direction, but the vector 3.up is always going to be along the basis y, so the local up direction. So here we'll say global transform dot basis dot y. Go back to the turning script. The object is the node. The method, we can use name of here, node dot lookout upwards. So the initial value is the old direction. The final value is the new direction, or the duration. So let's go back here. Export public float turn duration. We'll say this act of turning takes 1 second. Node dot turn duration. There's a few other parameters. There's a delay, which we don't need to use here. There's transition types, which is set to linear and easing in and out. We'll leave those in the default for now, but you'll want to play around with them. And you can export them as fields that you can change in the editor to see how they look. And then we call node.tween.start. Now as we're turning, there's two ways you can do this. We can go straight back to the moving class, or the moving state. Yeah, so we'll actually do that. We'll see how that looks. Let's say finite state machine dot set current state back to moving. And so if we go back to our moving state, let's explore. Let's create a float, private float, call it elapsed time. Every time we come back to the turning state, make sure we set the elapsed time back to 0. And during the physics process, we increment the elapsed time by delta. And here we say if elapsed time is greater than node dot, see what other duration here. Okay, move duration. So we'll move for 2 seconds, then drop. Move duration. Set current state to turning. Okay, let's test this. So the new direction is not just the XZ, because we need to transform it into global coordinates. So we go node dot global transform dot origin, and we can say plus or minus either way, but we'll say minus because we point the negative Z, so this is more correct, strictly speaking. Okay, that's better. Although he's colliding with himself now. So the problem is when colliding, the boss continues to ram against the object he's colliding against. What we want to do next is bounce off. So here we can say var variable collision info. So this move and collide function returns a kinematic collision object, which has information about the last collision. But you'll have to make sure that there is a collision before attempting anything. So here we'll say if collision info is not equal to null. So if there is a collision, what do we do? What we want is a bounce vector calculated that we can then pass into the turning state. So here, let's say private. No, we want this to be public actually. Public vector3 bounce vector. Now every time we come back into the movement state, we set this back to 0. Okay, so the boss starts moving again, sets this back to 0, and then he keeps moving, and if there's a collision, we generate a new bounce vector. So here we say bounce vector is equal to, first we pass the negative Z basis, which is the forward direction, and here we call the bounce method on that vector. And the normal is the surface normal of the collision, which you can get from the collision info object. So collision info dot normal, and use that, you normalize it. There you go. And then we set the state to turning. But how does the turning state know what the bounce vector is? Well, you have to pass it a reference of the previous state, which is this one here. So remember on our state, the enter function takes in an optional parameter called previous state, and by default it's null. But here we're passing this, which is this current state. And by doing that, we have access to this bounce vector field. And if there is a collision, we also want to return out of the physics process. We don't want to execute any further lines of code. Now back in our turning state, here we can say if previous is of the type boss moving, we give it a name called moving state. Here we can say the new direction and the moving state dot bounce vector, just to be safe, is not equal to vector 3.0. So in other words, we're making sure there has been a collision with the bounce vector generated. We can say the new direction, reset it to moving state dot bounce vector. So we don't need to use this block of code here. I could put it in an if-else statement, but this is good enough. One thing you want to make sure here is that the Y component of this is set to 0. Because the bounce might actually come off at an angle. So the boss might move downwards, you don't want that. This here also makes this line of code redundant, because a new direction is always being generated anyway. So we move this line of code down here. One thing I forgot to do is that we should normalize this direction. Otherwise it will move faster along diagonals. Yeah, this is a bit cleaner. Okay, let's test this. Okay, now you notice something. Once we're moving, the boss keeps turning into the wall. The reason that's happening is because it's going straight back to the movement state, and it's stuck in a loop, basically, between turning and moving because it's colliding every time. Here we'll say, in the turning class, we'll actually move and collide here. And here we'll say if the tween is still active, in other words, if we're still turning, just return, don't do anything else, just keep moving forward. But if it's not, then reset the current state back to moving. Okay, let's test this. As you can see, it's bouncing now, correctly off the walls. And off himself. Just a small error here. Make sure this is plus new direction. It has something to do with the orientation of the bounce vector. Alternatively, we could go back here and make the bounce vector, remove that, whatever works. Okay, I did a few tweaks here just to make things a little clearer. I just made the following segments a bit faster and made the boss segments a bit smaller. I also made another quick change, and I realized this works a bit better. In the following, when looking up, just make the up direction the global up direction, vector 3.up. And here you'll see no banking on the segments. So one other thing that you should do that I forgot to mention, check the collision layers. So we'll put this on the alien layer, and the mask, the things it collides with, we actually don't have to put it on any of these. If it were to collide with, so let's go level bounds for example, that's fine. But if it were to collide with any projectiles, the projectiles would be responsible for telling the boss that it's been hit. What this will do is stop the segments colliding with each other, with themselves. Yeah, you just have to tweak origins and things like that. And movement speeds, that's basically it. Okay, let's make the boss drop after it turns. Okay, so I took the code from the turning state. We can get rid of this, because if we're bouncing, we're not dropping. Now here, let's have a look at our new direction. So our old direction is just us facing forward. Our new direction is us facing forward, slightly down. So here, we can take this and just add the vector 3 down and multiply it by some nominal amount, like say 0.2. Now typically you shouldn't use magic numbers, so let's just put it here, float drop multiplier. You can swap this with drop multiplier. And this process will be the same. Let's go back to turning, and then after turning we'll change into dropping. So play, see how that looks. So he's turned, he's dropping now, and he's back to moving again. Turned, dropped. There we go, now he's banking. And I made an error earlier. So if we go back to our boss, we shouldn't be using the basis y, we should be using vector 3 dot up. Let's try this again. So turns and drops. Turns, drops, goes flat again. Turns, drops. Now there's another issue here. So as he's dropping, the basis stays downwards, so he's moving forward constantly. You can fix this a number of ways, but here let's change the order. So turning goes to moving, because turning always keeps you flat. And then moving goes to dropping instead. So we can say dropping. He's dropping now. Now as you saw, if you're not careful, something very annoying starts happening. Turning is fine, but after you drop and you turn, and especially if there's a collision straight after, what you'll find happens is that it starts to deflect either up or down. The first time I encountered this, it took me a long time to debug. What's important to remember is the lookout function doesn't actually point to a direction, it points to a point. So if you're moving as you're turning to a point, as you're doing when you use a tween with interpolate method, what happens if you already hit that point but you're still turning? Well, the lookout function doesn't really know what to do, so it does its best to orient itself to point at where you want it to, but it's already at that point. So a quick workaround for this is go into your dropping and your turning class, and here your new direction, you want to multiply it by some large number. Strictly speaking, best not to use a magic number here, but I will just leave a note. Just to say, we're multiplying that direction by 10, so that no matter how fast you're moving, you're not reaching that point before the tween is finished. And the same deal with the turning state. And so the behavior looks a bit like this. Turn, drops, turns. Collisions with walls, just turns. Collision with wall, just a turn. See him drop, then turn again. But he's always keeping flat in the XZ plane, which is what you want. Now in the boss, here we'll say min height. I'm going to set this to 0.6 units. Probably better ways to do this, like with a collision shape perhaps. We'll just keep it simple for now, so we can say if node dot global transform dot origin dot y less than or equal to node dot min height. We can say f set current state to keep him turning, and we return. So we don't execute the remaining functions. So as you see there, instead of dropping, he just turned. 0.6 is quite low in this case, so we'll make it a bit higher. Maybe we'll just make it 1.5. Very good. Next, let's implement destruction. I'll give you a quick look at the destructible class. Basically, there's a protected property called health. Whenever it takes damage, which is a public function, it passes an amount and subtracts it from the health. When health reaches 0, the destroy function is called, which is just queuing freeing that node. Here we want to override this, and we'll say public void destroy. Because remember, this inherits from just destructible. Set current state to destructing. Now the reason I implemented this as a state is if you have any visuals about how the segment gets destroyed, if there's a particle explosion, what you can do is delay the freeing of the node until after that the particles stop emitting or the tween is done. But I'll omit these details here. What all we want here is we want to update all the adjacent segments. So on the boss object, we should create another method. And here we'll say public void update connected segments. And here we say if segment in front is not null, you can say segment front segment behind is null because this segment is being destroyed. And we call the segment in front dot update segment method. This will update its visuals and its state. And similarly, we check to see if there's a segment behind. We say segment behind, segments behind, segment in front is null. So there's a segment behind no longer has a segment in front of it. Okay, so if there is a segment in front, make sure that that segment knows there's no longer a segment behind it, and update its visibility and behavior. Ditto for the segment behind it if there is one. Then we go back to the destructing method here. So remember when the segment gets destroyed, it goes into this state. And here we can say node.update connected. So this updates the connected segments. Then it just calls node.queueFree. Okay, let's test this. We'll try and hit it in the middle. Didn't appear they were two separate segments, but they are now two separate segments. Yeah, need to tweak the intervals so it appears that they're changing more often. Okay, very good. We're almost there. So we've handled the breaking of the worm and the destruction, the following, basic movement, dropping, turning. That only leaves one more state, so we're almost there. Firing. Now let's make our control flow behavior such that it fires once, then it drops. So here we'll say private bool previously fired. Now by default we'll say previously fired to false. Okay. And here we say if previous is boss firing equals true. Okay, now here we've got the move duration. So we'll say if previously fired, set the current state to dropping, else set the current state to firing. That's all we need to do. Now let's go to the boss firing class. Now although we have a boss firing state, it's up to you if you want to implement the firing method on this state or on the boss itself. Similarly, it comes down to visuals and other complex behavior. I'm just going to put the fire function on the boss instead. Here we can say node.fire, oops. So just call the fire function and set the current state to moving. And remember, we need to pass a reference back to the moving state saying that the previous state was firing. So next time, drop. Okay, here we'll implement the fire method. Fire. Okay, let's take a look at the projectile scene, which the player uses as well. Now the projectile, what it does is, all it does is it moves along its Z basis, so the direction it's pointed at, moves forward. If it collides with an iDestructible or an object that implements the iDestructible interface, it calls the take damage function on that object and it passes its own damage value. Then it destroys itself. There we go. Now here, the layer this is on is projectiles player. It's actually unnecessary to distinguish between projectiles player and projectiles alien, and I'll show you why this is the case. In fact, I'm actually going to remove it from this layer. What actually matters is the mask. So this projectile, by default, it's called from the player. So it should only interact with layers 4, which is the aliens, and layer 5, which is the buildings, the shields that are destructible. Here we're going to export a hacked scene called projectile scene. Let's hit build and we'll pass the scene in here. Let's go back. Here we'll say projectile. We can just say variable projectile instance is equal to projectile scene dot instance. And here we can say, now remember the boss is moving, so we don't want to add child directly. The boss will be attached to the aliens node here, which doesn't move. So back to our script, we'll say get parent, our child, the projectile instance. And now that it's in the scene tree, we can update its direction. So we can say projectile instance dot global transform. Here we should actually say as projectile. Is equal to this global transform. In other words, we want the instance object to have the same origin and heading as the boss segment. And here we want it to aim at the player, which if we go up the tree and down again, we'll find the location of the player. Now because this is a simple scene, I'm just doing this by getting the parent and then getting that node, but you should be a bit more careful with your project scales. There are better ways to handle this. Here we can say player origin, player or player transform, let's say, is equal to get parent dot get node player as player movement, not strictly necessary, we'll just say as spatial. And here we can say projectile instance dot look at player transform dot global transform dot origin. So just look at the player. And here we can pass any vector that's perpendicular. We can say projectile instance, you can pivot it up its own x axis. Doesn't matter too much. Now if you try and run this, what's going to happen is it will destroy itself because it's instantiating that projectile, but that projectile is designed to attack aliens. Need to call get parent twice. Yeah, and as you can see, it destroyed itself, the head. Okay, good, but it is instantiating the projectiles. Now this is how masks work. See how this has a bit value and an integer value? Bit 3 just means 2 to the power of 3, which is 8. So 1 is actually bit 0, 2 to the power of 0, which is 1. 2 squared, value 2 to the 1 is value 2. 2 squared, value 4, etc. So what we want this projectile to interact with is the player, which has a value of 1. We want it to ignore aliens. We want it to damage buildings as well, which has a value of 16. So here we say projectile instance collision mask is equal to 1 plus 16. So we'll keep this explicit. We'll say 1 is player, 16 is buildings. Good, now it's firing upwards. Okay, so if we go projectile, instead here we go -z and player fire, we'll fix that as well. Let's restart that. And as you can see, I got destroyed, sniped by the, the alien. Very good. So let's try splitting the worm. So something funny happened. Every time I fired, I got destroyed myself. The reason is, as I showed you in episode 6, I implemented an object pool, which means that the same projectile the boss is firing, I'm actually recovering from that object pool and firing again. What's that actually? And so that means that projectile is programmed to collide with me, not the alien. So back onto the player fire here. I have to update this collision as well. And we want this to interact with aliens and buildings, which is 8 and 16. Keep in mind on my main project, this is a lot cleaner because I made the projectiles responsible for, there we go, made the projectiles responsible for initializing themselves with the correct collision layers and directions, so I didn't have to worry about it. There we go. Now I've split the segments, so we should get fired at twice as much now because we've got 2 heads to worry about. As you can see, that is the case. Yep. Now because of the logic here, they don't have enough time to drop because they're firing and then it's another 4 seconds, but before that happens they actually hit a wall and turn. But the 2 heads are moving independently as we saw earlier. Very good. And we crashed a bit earlier because we're not checking if this player is a null reference. When the player gets destroyed, that reference becomes null. So you have to be careful with that. But other than that, congratulations, you've reached the end. This is a very long video and I apologize for that. Hope you took something away from that. How to implement an Eater of Worlds type worm boss. I showed you how to make it move, bounce, you know, attack the player, which is not something that I showed earlier in the earlier videos, and how it, most importantly, how it breaks off into segments. So I hope you enjoyed that. And thank you for watching if you've made it this far in the 11th episode now in the devlog tutorials for Andromedoom. I've shown you how to implement the prototype completely. Moving forward with this video series, there does seem to be a bit of traction on the videos, but I will split the videos now, including starting from this one. I won't put tutorials and devlogs on the same video, rather I'll make them into separate videos. So I'll be continuing with the devlogs on the main project, and anytime I get an idea for a tutorial, something that I've put together that I think is worth sharing in Godot C#, I'll make a video about that. I'll see you in the next episode where I'll be presenting all of the aliens that I've put together for the bathymetroids, and then the episode after that, the player ships and the weapon system. I'll see you there. Thanks guys.